Hello everyone. I'm Stefanos Cornelius Mitspitidis, SKMP, whatever. I've been deeply involved with Dreamcast simulation, and I know a lot of details about the Dreamcast. And over the past few weeks, actually it's just on and off days, I've been working on this verilog implementation for a part of the graphics card, the core. It's named core, which is not very helpful. Um, so this is inspired based on the work that Electronas did, and I had a lot of help from Electronas and Korn, and yeah. So this is a small presentation I prepared. It's not very refined. I'm just gonna do it without any preparation, so here's hoping for the best. So let's start with a recap of the Dreamcast hardware. This is a technical presentation, and I assume that you understand how Dreamcast works, but it always helps to refresh the basics. So the Dreamcast has three important chips. The SH4, that's an SoC that was an off-the-shelf component. It contains the main CPU, DMA engine, DRAM controller for the main memory, some stuff. Then this part. Nope. Then there is the memory RAM, the main memory. Yeah, something not working right on my mouse, but that's okay. Then there is the main memory that is connected to the SH4, and then there is the Holy chip that contains the PowerVR tile accelerator, the PowerVR core, which is the part we have implemented, the system bus, a secondary DMA controller that drives the main, that coordinates with the main SH4 DMA controller to copy memory around, then the video output part and some other things, and then there is a third chip that is the ICA CPU chip. It contains the sound CPU, the sound core, and a DSP. Connected to the Holy, it has a second memory controller independent of the main memory controller, are two banks of video RAM. Those can be read as two independent 32-bit banks or as a single 64-bit. And that's a bit of a pain for us to emulate because we have a single memory bank, DDR3 on the D10, but it's okay. There is also sound RAM that is connected to the ICA chip with another memory controller, and then there is the GD-ROM, the BIOS, and some other peripherals that are connected to various places, like some of them are in the main CPU, some of them are on the ICA, some of them are on the Holy. It's a little bit complex. But roughly, that's a high-level architecture of the Dreamcast. So we are, of course, focusing on the core. So let's refresh our memory of how the GPU works. This, for me, is work that has been done mostly for the reference rasterizers, my software implementations. I have three of them. The second version, RFSW2, the third version actually, I think is quite accurate, but it still does a lot of things differently than the real chip, of course. So high-level outline of the core. Primitives, unlike traditional renderers, in the deferred rendering mode that Dreamcast uses, stores primitives in video RAM, and then also stores links pointing to those primitives for its tile. So it does a bounding box intersection test, and then it decides which tile gets its primitive. Since it's a bounding box, sometimes you get triangles that aren't actually in this tile, but it's what the hardware does. It's good enough. Then you also have a region array that points into a list of tiles, and for each tile it points to the list of primitives. There are 5 list types: opaque, punch-through, modifier volumes for opaque and pass-through, translucent and translucent modifier volumes. Opaque is like normal geometry that you can't see through. Punch-through is alpha tested, so you can have holes in it, but you can't blend it. Modifier volumes, they can apply either a shadow or change the color and texture with some limitations, but yeah. So you render them on top of your scene, they're not directly visible, they just affect the previous scene. Translucent is alpha blended, and translucent modifier volumes apply to translucent alpha blended also, only, not also. And the hardware does depth peeling to sort the translucent layer. That means that they are rendered from back to front order, so they blend nicely. Punch-throughs are actually sorted from front to back because you don't have blending, you can only have holes, so that's an optimization. Um, so in general, the hardware starts with the region array walk. Then for lists in every tile, for lists in this tile, it walks every list, it rasterizes on the ISP. ISP is the depth processor. There are 32 depth processors. That is fairly fast. The rasterization of the whole tile is done in 32 cycles, supposedly, on the hardware. That's what the documentation says. There is also some triangle setup that needs to happen that happens in 14 cycles. Some of this is in parallel. We don't exactly know how the hardware works. Anyway, once the list is done, then you create spans, which specify which triangle and how many pixels. Then you sort them so that all spans of the same triangle come together. That is in order to improve the texture cast performance in the TSP. And then the TSP gets this sorted list of span, and for every pixel, it saves 1 pixel at a time. It has some small caches for the textures, does color calculations, and then you move on to the next list, and then to the next list, and then to the next list. This is a very high level approximation. In reality, Opaco and punch-through are done first, then you do the modifier volumes to decide if you are inside or out, and then you do the shading. But this is a high level overview. Then once you do this for all tiles, including the translucent, which have to be passed through many times for sorting, you write them out to VRAM. There is X and Y scaling happening there for anti-aliasing and flicker-free intralace scan, I guess. I haven't implemented those parts either in this chip. And then you proceed to the next tile. Then once you do this for all of the tiles, your frame is done, and you notify the game, and then the game on the next VBlank presents the new frame buffer to the user. So let's see how polly2-rtl implements this. I have put a link into the description of the video and also in the presentation with the exact matching code. There have been a couple of implementations and code is moving fast, so if you want something that matches this presentation, you better use that. So, of course, polly2-rtl is just the PowerVR core. It's not the tile accelerator or the rest of the hardware. So we have a software emulator that we call Minicast. It's based on an old version of Raycast, forked a couple of years ago. This was originally done for Electron Ass's work. It runs the SH4, the tile accelerator, the DMAs, the sound core, the sound engine. Even though no sound is produced, you still need the sound engine in order for the games to not lock up. There is no DSP to save time and everything else. The video RAM is stored in the shared DDR3, and it is mapped through /dev/mem in an uncast way, so that all of the writes are visible by the FPGA. This actually is a performance problem because in many places the code assumes that it can read back fast from the video RAM. So we had to address some of that, and some of that is also inherited into the design that we are going through. In a normal Dreamcast, you have both cast and uncast mirrors of the RAM, and the tile accelerator is a chip. It's on software, so it's a little bit tricky, but it works. Then on the FPGA, the core gets the lists that the tile accelerator has prepared, and the region array that the game has prepared. The region array is independent of the object list that the tile accelerator creates, and it renders those. So that's kind of how this works. A quick outline of the project. We do implement most of the pipeline, namely fog, bump mapping, pixel clipping, scaling are missing. Fog is a little bit tricky, but can be done. Bump mapping requires a couple of multipliers. Pixel clipping and the scalers are also kind of cheap. The white filter is more complex. It's a 3-tap filter, and it's not as much used. We will see. Um, we don't support punch-through polygons. We sort them as if they were translucent, because waiting for the TSP to finish to figure out if a pixel is visible or not in our architecture is actually slower than just sorting them. Depends on how many layers there exist, but this allows us to run many things in parallel, as we'll see in the next slide. This is a little bit slower. It's mostly the same visual output. There are some tricks you can do with the punch-through polygons because they don't work exactly like translucent, but I don't think any game is doing them. I've tested it on the real hardware, so we know exactly how that part works. Yeah, I guess not important. It's also important to state that this is like a heavily inspired by the Power VR implementation, and it's not fully faithful to the Power VR chip. Clocking is different, different trade-offs. For example, we only have 4 ISP cores, not 32, because we could not fit 32 in the chip. Each ISP core is essentially 3 multiplies and a floating point add. The floating point add is 1K ALMs. We don't have that many DSPs, we don't have that many ALMs. So how does this work? It works in a similar way to the Power VR chip. You can see the units, the register array walk, then the object list walk. Those are fairly simple. You just read the pointers. You will notice there are a lot of FIFOs and AB buffers to allow work to happen in parallel. In the first implementation, there weren't any, and it was 3 to 10 times slower. So this was added earlier this week. So yeah, then we have to fetch the primitives. We have to do the math to figure out the plane equations. These identify which pixels for the ISP, which pixels belong in the triangle and which do not, and also the depth interpolation. Then we store those planes in a FIFO so that the rasterizer can process them as fast as they can. Sometimes you get a lot of plane equations at once and the rasterizer is slow in a primitive, so it's nice to have a queue. Then the ISP rasterizes them 4 pixels at a time, so it takes up to 256 cycles, worst case, if a triangle covers the entire 1024 pixels. We do have some optimizations there, like early rejection. If a triangle is not at all in the tile because of the bounding box, it can still happen and be contained in the list, but it's not visible. There's also bounding box optimization, so we also early reject and only process the pixels that contain this triangle in this tile. Then this writes the buffer, and then we go to the span creation. While the ISP rasterizes one pass, the span creation works on the previous pass. The span creation processes up to 4 pixels at a time, creates span that are 4 pixels wide. We could do them larger, but it's fast enough. There are some limitations and some optimizations that can be done there. We don't also do span sorting. Instead, we have much larger texture caches than what the hardware has. Then there are 2 FIFOs. The span creation finds out which primitives exist in this tile after, because some of them have been hidden. Like ISP only tells you which pixels are visible at the end, and then you only process those pixels for shading. So then you have to fetch again the TSP parameters like the color and the UVs for the vertices. ISP fetching only fetches the depth and the XY, Z coordinates. Well, XY inverse W, but yeah. So this happens in parallel with span creation. So there is a FIFO there that then fetches, that then feeds the fetcher. There is then another FIFO that feeds the TSP setup. This also happens in parallel with the span creation for one tile. And these write out to two ring buffers, one ring buffer for the TSP setup parameters. These are the equations to interpolate the U, the V, and the up to 8 colors, 4 colors for base color, 4 colors for offset color. Uh, this is a ring buffer because we need to support up to 1024 pixels because technically a tile can have a different triangle in each pixel, a different primitive in each pixel, but that's very rarely the case. Usually triangles, usually tiles have like 30, 40 triangles at most, sometimes just 2. So we have 5 buffers there, and we have enough room, 1024, for both TSP setups and spans for the worst case, but in practice, much less is used. So it's a ring buffer, so we can queue up multiple uh, passes to the next stage. So the pipeline can run like up to 8 passes ahead of the shading step. That might even be at the later tile. Then there is TSP shading and texturing. So this rings from the ring buffer. It interpolates for every pixel the UV coordinates. UV coordinates are the addresses in the texture, if you don't know what that is. And then it fetches from the texture cache. If the texture cache misses, then you have to wait for the stuff to arrive from the DDR3. That's the only thing that stalls the TSP. Otherwise, it does 1 pixel per clock. And this writes to a buffer, and this is also a double buffer, so that the previous tile can be written out to video RAM while the current tile is getting processed. So we can have several tiles, several passes processed into several passes in process before the TSP processing, and then we can have a tile after the TSP processing that is the previous tile. There is also a DDR3 arbiter. There is some glue logic to glue all of this together. All of this is around 32,000 ALMs. That's around 75% of the chip. With the HDMI output and the MISR framework, we get 95% chip utilization. That's something else we want to look into, trimming that down. We also use around 4 megabits of MTK, around 70%, I think. I don't remember. We have a lot of more memory available. Clockwise, the ISP path clears 81 megahertz. I've done a small pass over it. It was 35 megahertz, then it went to 81. The TSP setup is just 31 megahertz. I haven't optimized this. And the TSP and shade and texture is 102. I went a little bit OCD on it and it's quite fast. Also, the setups, they can do, like the triangle setup for ISP, can do one primitive every 14 cycles, and for TSP every 52, 58 cycles. Those numbers, they're likely to go up as things get more complete. We will see, because we have some glitches and we need to widen some paths. For testing, we run the clock at 61 megahertz. We kind of overclock it over the 31 megahertz clearance target of the slowest path, the TSP setup. But it kind of works. It does lock up once every 2 minutes, and then you have to reset, and it works and continues working for 2 minutes or so. Depends on your luck. That's one of the things that I want to look at. So as I mentioned, we do a lot of work in parallel. Here you can see in red the states that can work in parallel. So we read the object lists while we are fetching the primitives, while we are doing the setups, while we are rasterizing, while we are creating spans, while we are fetching the TSP primitives, while we are doing the TSP setup, while TSP shading and the tile is written out. All of this parallelism is required for the hardware to hit the targets, and we are still clock for clock slower than the original hardware. So there's quite a bit more to be done there. A quick note on the FIFOs, there's many. They are big, they are a little bit wasteful, and the DDR3 arbiter is simplistic and not very pipelined. It doesn't, you could issue a read while waiting on another read, but we don't do that yet. I don't want to get into more details. We will take a quick look on the code later, and I guess you can go read the verilog if you're into that. So, the kind of optimizations implemented like today is that uncast VRAM accesses, as I mentioned, were killing us. This has been addressed by keeping copies of important structures in shadow memory. This gets us around to 60% performance from the software emulator as an upper ceiling for heavy games like Dead or Alive 2. Some games run full speed, the BIOS can run twice full speed software-wise. There are some further optimizations I have in mind that can get us up to 80% in Dead or Alive, but this will not run 100% for heavy 3D games, so there is, even without the problems on the rasterization step, like the core part, without the speed limits there, the ARM core alone cannot pull this off for every game. Another thing we have is the early tile rejection that I mentioned. So this is one extra step before we process the tile, the ISP tile, that removes triangles that are actually not in this tile, even though the bounding box says it does. Another optimization is a sort cache. This also exists on the real hardware. So what this does is quite smart. As it draws and it sorts the pixels for every layer of the depth pass, once a triangle has no more visible pixels, so it's fully occluded behind the geometry, then it no longer reprocesses a triangle. I have that as a proof of concept. It cuts down rendering by around 20% in heavy blending. But the problem is that the current implementation uses too much logic. We needs to become MTKs, and MTKs can only have one read port and one write port, or two read ports, but who uses that? Anyway, that's something for the future. Speaking of the future, the next steps are cleanups, putting things in repos in a way that makes sense, and having instructions for people how to build this and contribute. Then the next step is to widen the triangle setup to 23 bits mantissa. Currently it's 16 bits because that's what we can get in a single DSP unit, but as you have seen in the videos, the triangles are swimming around, especially when they are very close to the camera. The PowerVR GPU in the Dreamcast is very odd about this. It can handle very big coordinates, very close to the camera, and it fixes up in the FPU somehow it handles them, so we have to do the same. Other consoles or other GPUs of the same area actually relied on software clipping those triangles, but Dreamcast doesn't, so we have to deal with it. Then another thing is supporting quads. Quads are not 2D, they're actually fully 3D primitives in PowerVR. They're like planes. And they are used for 2D elements or particle effects by games, so that's why many UI elements are missing. Then a lot of code was written by Claude. This was a lot of prompting for me. So that needs to be reviewed, cleaned up, fine-tuned, thinned down, actually get the human in the loop. Then getting to hit 100 megahertz so we can run it fast. Make minicast support things like input and disk selection. Right now you have to SSH to your mister, and input comes through SSH and it's very not interactive, but it's good enough for testing. And then further away, like iterating on the architecture, getting better clock for clock performance, whatever. I don't actually have a timeline. This is a passion project, so we'll see. I'll try to work it on the weekends. So I mentioned Claude was used, so I figured I might as well clear up how this was done and how Claude was used. Most of the Verilog code has been written by Claude. I've written like 20 lines of Verilog. I have reviewed the TSP unit, that's why it's so much faster, like the shading of the TSP, shading and texturing. I'm using Opus 4.8, not Fable, because Fable is slow, and I'm using the non-thinking variant, so I can stop it when it goes the wrong direction. The thinking variant doesn't tell you what it's doing, so it's too slow, and it's off the weights. The code is pretty bad at some places. I think 10 to 15% trim down in the ALM usage can be done. I noticed in the depth buffer it does some complex computations because it assumes full floating point, but we know that things aren't signed, for example, so we can just do an integer compare in our units. Uh, that's one example. There's many. The code is also unintuitive. I picked a weird pipelining setup where there is no input or output buffers. I think I'm gonna add output buffers to all of the units so that it's simple to read and simple to write. This is the second iteration. The first port, it was just test and Claude writing the code. That was 3 to 10 times slower. Now, this I fully architected myself based on what I saw being slow and what I assume the hardware does. Yeah, the whole board has been done in a week or so. Oh, and we used a lot of verilator. Verilator compiles Verilog to C++, and then you can quickly iterate. Synthesizing the project with Quartus takes around an hour if you're like 30 minutes. So that's not very easy way to test. Plus, with Verilator, you can add all kinds of hooks and debug logs. So Verilator, test fences were very instrumental. Also, Claude tends to write bugs, so having tests is the only way to make it useful. Yeah, let's take a look on the code. So I have it here open. I have the link to the repo. There are a lot of files that are not used, and there's also a lot of junk files in my local copy. So RTL PIL-core is kind of the entry point. We had the previous core but didn't do layer peeling. That's why this is called PIL-core. You can see there is also ISP core somewhere around here, but it's not really functioning anymore. And from here you can get like a high level design. I'm not gonna go line by line, that doesn't make sense. You can see there is the typical pattern of Claude writing comments that sometimes make sense, but over time they don't. So that's another thing to remove. So PIL-core instantiates the main unit, which is the ISP setup, which is streamed. It accepts a new primitive every 14 cycles. There is some pipelining going there. This is the ISP rasterizer unit. The PIL buffers. This is actually the depth and some more information. It's not just PIL buffer, but naming convention is all over the place. That's another thing to be fixed. Yeah, a nice thing to look at. Yeah, the span buffers, the spanner module. So you can see this has been cut in modules in some places better than others. Some things to look at are the TSP shade pipeline version 2. This is actually quite easy to read. So you can see here the different stages. These are all the pipelines. Then there is the interpolation unit, the mipmap level unit. This has been cut down in small units so that you can understand what's going. The units don't actually carry down the register, so you have to write delay loops like this to synchronize the rest of the parameters you want to carry. The texture unit, etc., etc. On the code base, it's a little bit of a mess, but most of the code lives inside the TSP. You have to read the code or use some AI to figure out which modules are actually used. Here is the ISP core. It's inside the TSP folder for some reason. Yeah. Let's take a look on the color combiner, for example. So this is a fairly simple thing. For every clock. It does the multiplies. This also has this multi logic because these are 8x8 multiply units. We don't actually use a DSP, so we save them for the triangle setup because there we need two of them per equation, per clock. Yeah. So that's kind of how this looks. These are some, like this is the spanner that takes the buffers and does the spans. Yeah, so I plan to go over this code and rework it. That's the next step. Clean it up, and then, yeah, we'll see where this goes. Eh. Okay, so that's it for now. I mean, I told you at the beginning, this is a very unprepared, very rough presentation with many mistakes, but just wanted to get something out there for people asking for more technical details. Here you can see the hierarchy, and I cut down to the important units, so you can see kind of the use. The interpolation is using a lot of DSPs. The texture units are using a lot of DSP blocks. This is to do the address calculations. So you need to fetch up to 4 texture textiles at a time because of bilinear filtering, and then you need to calculate 4 addresses, and we have 4 caches. Yeah, I guess that's it. I'm gonna see if there are any questions or anything. Okay, so SH4 asks, if we had a bigger FPGA, if we could do the full 32. Yes, we could do 8, which would be a big improvement. We could do 32, but instead of 32, because we have some other, like this bounding box checking makes it faster, like inside the tile bounding box, apart from the bounding box for the per tile work, for the global tiles that the TA does, then for each tile we do a bounding box for which pixels are potentially covered. This saves half of the time. So we are around 100, 120 cycles versus 32. It's not terrible. Then we have the full tile rejection that cuts down the numbers further. So I think with 8 or 16, we would reach the same performance as the original chip has. If I had such a big chip, I would much rather implement the tile accelerator in it, though. Yeah, the ISP rasterizer is not doing anything fancy. It is checking every pixel in a tile. You also ask about a Pinedilla style rasterizer. I don't know what that is, but I can tell you what we do. We calculate the plane equations, and then we do 2 multiplies, add them together with a base constant, and then check if it's positive for all 3. Well, this has to become 4 planes for quad support. Quads are a little bit tricky. Maybe we just make them slower. Routing contention, we don't get much. Routing utilization peaks at like 40% and average is like 20. And yeah, the queues get full, get empty, depends on the tile. Also, there are some really pathological scenes like in House of the Dead where half of the scene, all of the queues are full, and then the TSP is the bottleneck, and then on the bottom half of the scene, the opposite happens. So it's kind of hard to debug. I plan to make some tools that make this easier to visualize and understand, and more logging, like heat maps per tile, per passes. I will actually showcase some tools that we already have just in case. And yeah, there is a test harness. Actually, I think I can show this live. Let me see. So if you go in the simplex folder and you do this make frontend tsplp. This is the test handlers, and then dump is optional. You can find the list of dumps in dumps folder. There's quite a few. And here it compiles everything with verilator, and assuming that works and you have the right verilator version, you can see it processing the tile. It gives you reports that this happened, and it's not very fast. This is just for a single frame. But this is my typical development flow. It's like do something, run 10 dumps, see the reports. At the end of every rendering, there is a report. Let me also make this bigger, I guess. Yeah, so you can see here, like the ISP took this many cycles and was busy 80% of the time. The spanner took this many cycles, the TSP this many cycles. There are some occupancy reports for how much things were parallel. Then the number of triangles that were trivially rejected. Then some more breakdown of cycles. Some of the statistics are not very relevant anymore, but many of them are. And here are the cast statistics, and then you can open the resulting render, and you can see this is like these wrong triangles are because of the triangle setup precision, for example. It's picking the wrong vertices or something. It's a little bit tricky what to do. Yeah, let me check if there are any other questions. Oh, a lot of stuff in the chat. Yeah, I don't see any other questions yet, but I think the stream is quite behind a couple of minutes, so I'll let it run. Ah, funny. Now the cursor works, now that I don't need it. Yeah, so as always, go check out the GitHub. Uh, Find me on Discord, like either on the emudev server or the Mr. server. I'm SKMP. Yeah. Vegeta, that's a long story. I don't know. I lived a few years aboard. That has helped. All right. So I hope this was good enough. Again, this was a very unprepared. I just thought I have some free time. I don't want to write code. Uh, let's make something. So yeah, this is, by the way, one of my favorite programming related memes. So that's all. Enjoy, and I'll try to keep you updated next